Welcome back to differential equations. In this video, we're going to be looking for power series solutions to differential equations. Specifically, I'm going to be looking at solutions to second order linear ordinary differential equations with polynomial coefficients. Right? Polynomial coefficients is a little bit weird. I'm actually going to restrict it slightly more than that. I want to look at equations in the form y double prime. I'm going to deal with y as a function of x. I really find that power series make more sense to me. I'm more comfortable with them when I'm dealing with functions of x instead of functions of t. Then I need some function p of x times y of x. I'm sorry, that should be y prime of x, and some other function q of x times y double prime of x. And I'm going to set this equal to 0. So P and Q are both going to be polynomial functions for what I'm doing right now. And I do want to point out that there is an implicit coefficient of 1 on the y double prime term. If that was not a 1, if that was something more involved, then we would start having issues. If P of x and Q of x were something more complicated than a polynomial, we could start having issues. We will look at that in a future video, but for right now, we'll deal with the simplest case. I also want to mention here that there's not a lot of application to power series solutions for differential equations. Some textbooks try to build this idea up and make it feel like it is a big thing that you're going to really need to know if you're going into any work with differential equations, when in reality, there's about a dozen different differential equations that are susceptible to solutions of this form, and for the most part, it just doesn't come up. The reason that we care about it is that some of those equations are incredibly powerful, and there's a lot of different application, a lot of different mathematical models that turn into differential equations that can be solved using power series methods. We call the solutions to those equations special functions. And having a library of special functions and being competent with not just what they are, but recognizing the equations that they come from is an important building block for many different paths that lead past differential equations and into different applications. So yes, we are going to be able to solve differential equations in this form. No, there's not a lot of different differential equations that can be solved, but that's okay. The theory and the background are important, and the couple of equations that straddle that balance of we can solve them and we have enough time to solve them are a great testing ground, a great place to work out the basic theory behind these ideas. So let's look at about the simplest thing that we can look at. First of all, let's fix these. That's supposed to be a first derivative. That's supposed to be a constant. I had a couple of stray pen marks that made everything look weird there. Sorry about that. But our goal in this process is we are going to assume that y of x is a power series. The sum k goes from 0 to infinity of a sub k times x to the k power. Then I can take the derivative, y prime of x. And let me write this down first, and then we'll analyze. Where did that come from? Taking it piece by piece. Remember that a summation means addition, and the derivative can distribute across addition. Derivatives are a linear operation. So instead of trying to take the derivative of the entire sum, we can take the derivative of each piece. AK is a constant, so it just comes down. And the power rule tells us that the derivative of x to the k is k times x to the k minus 1. And then I changed my starting point. Instead of starting at k equals 0, I started at k equals 1. Well, that's a little bit more obvious. There's two ways to think about that, and they come out exactly the same in the end. If you go back to the original differential equation, what does the k equals 0 term look like? Well, plug in k equals 0, you get a0 x to the 0, which is just a naught, a constant. The derivative of a constant is 0, and I don't want to add 0, so I just skip that term. The other way you can think of that, well, if I tried evaluating this expression at 0, well, that k there would just give me 0. So the first term is doing nothing. I can cut it out of the summation, and I can start my sum at 1. The reason that starting my sum at 1 is so useful is because it turns out that having a power other than k on your variable is kind of messy. So I'm going to perform a change of variables, letting n equal k minus 1. Looking at the lower limit, when k is 1, we'll plug that in and you get that n is 0. When k is infinity, n is still infinity, so I don't have to worry about the upper limit. And playing a bit of a rearrangement game, k is, of course, n plus 1. So I can rewrite this series as the sum n goes from 0 to infinity of a sub n plus 1 times n plus 1 times x to the n power. And the advantage of doing this, again, is that I now have something that looks like a power series, x raised to the index power. The disadvantage is I now have k's and x's going on, so I make a change of variables. I change back to k's. I just let n equal k and just switch it over. So I now have k goes from 0 to infinity of a sub k plus 1 times k plus 1 times x to the k. When power series come up and when working with differential equations and power series comes up, that is a manipulation that you tend to see done immediately without any commentary whatsoever. It's not obvious. It takes quite a bit of thought to figure out what just happened. But now that I've gone through and shown you how it works, I'm going to be much quicker when I do it again for the second derivative. Because I can use the same logic. Taking the derivative of a power series leaves the coefficients. AK plus 1 and k plus 1 are both constants. They get left alone. The power rule tells me that the derivative of a to the k is k times x to the k minus 1. And then I can change variables twice, but not really mention the middle step, and rewrite this as k goes from 0 to infinity of a k plus 2 times k plus 2 times k plus 1 times x to the k power. And again, I'm doing the same change of variables I did before, replacing k minus 1 with n, and then rewriting and replacing all the n's with k's so that I'm using the same index throughout the process. It feels kind of like cheating, but it works. And the important thing here is that I've gotten everything to have that same x to the k power throughout. let's turn to a specific example here. I'm going to look at y double prime plus x times y is equal to 0. This equation is known as Airy's equation of order 1. Being able to classify it, being able to name it, not that important, but it is an equation that has a name, so I guess I should name it. And I'm going to use the same ideas that I used in our previous discussion. Y double prime is going to be the sum. K goes from 2 to infinity of ak times k minus 1 times x to the k minus 2. And of course, y itself is ak times x to the k. And why didn't I use the version where all of the x's had x to the k? Why am I using the version before the substitution? The answer to that is I have an extra x here that I need to deal with. But because the summation is on k and not on x, x is a constant with respect to the summation, and I can distribute it through. And now we start to see where the problems are going to come in. Because all of a sudden I now have indices, I now have exponents of k minus 2 and k plus 1. Right? So I'm going to do a different substitution on each of these. And this is why you go to that base case, right? Take the derivatives, plug it in, see what else is there, distribute through if you can, and only then do you do the change in variables because you never know what you're going to end up with. So over here, I'm going to let n equal k minus 2. Over here, I'm going to let n equal k plus 1. And that will give me the sum. N goes from 0 to infinity of a n plus 2 times n plus 2 times n plus 1 times x to the n. The second one over here, I will have n goes from 1 to infinity. Right? If k is equal to 0, then n is equal to 1. And I will have a n minus 1 times x to the n. Right? That idea of changing variables inside of a summation is tricky. It takes some getting used to. So take a couple of minutes, make sure that that step makes sense to you before you continue the rest of the video, where the next trick is going to be to notice that my sums start at a different index. If I take that first sum and I break out the n equals 0 term, well, when n equals 0, I get a 0 plus 2, which is a2, times 0 plus 2, which is 2, times 0 plus 1, which is 1, times x to the 0 power. Then I can take the rest of the sum, n goes from 1 to infinity, and leave it in the summation. Now that I have done that, again, those first term plus the first summation is just the old first summation. But the advantage is now I have the same summation going on here in both of these places, so I can combine them and write it as a single sum. Right? So all this stuff in front I can clean up. 2 times a2 times 1 times x to the 0, that's 2a2. And then I have the sum. N goes from 1 to infinity of a n plus 2 times n plus 2 times n plus 1 times x to the n plus a n minus 1 times x to the n. And one last step, I'm going to factor out the x to the n inside of the summation. So the sum, n goes from 1 to infinity of a n plus 2 times n plus 2 times n plus 1 plus a n minus 1 all times x to the n. At this point, we use a result from linear algebra that we have used in the past to great success. The only way for two polynomials to be equal to each other for every value of x is if the corresponding coefficients are equal to each other. And I know that power series don't look like polynomials, but power series are polynomials. And so I can take the coefficient on x in every step of that sequence, and they all have to be 0. So I get that 2 times a2 must be equal to 0. And I get that a n plus 2 plus, I'm sorry, a n plus 2 times n plus 2 times n plus 1 plus a n minus 1 must also be equal to 0. Rearranging that term gives me that a n plus 2 is equal to the negative of a n minus 1 all over n plus 2 times n plus 1. And this relation will be true when n is equal to 1, 2, 3, and so on. It's not true for 0 because our sum starts at 0. And because it's based on this summation, it's true only for integer values of n. It only makes sense for integer values of n. And so thinking back to my original assumption, I know absolutely nothing about A0 and A1. I know that A2 is 0, right? Well, 2 times A2 is 0, but divide both sides by 2. And then starting at A3, right, when n equals 1, this gives me A3. I can relate A3 to A0. I can relate A4 to A1. A5 gets related to A2, A6 gets related to A3, A7 gets related to A4, and so on and so on. I can figure out the higher orders of the coefficient based on knowing the earlier ones. We call that sort of a rule a recurrence relation. In this particular case, I need to know A0, A1, and A2. And so to make sense and try to get an idea of what's happening, it's going to be convenient to write out 3 columns, A0, A1, let's move that A1 over a little bit, I'll need some more space, and A2 is going way over here, and we'll see why that makes sense in just a few moments. because of course A2 is equal to 0. That's something that we knew before the recurrence relation. Then A3, if I plug n equals 1 into my recurrence relation, I get that this is going to be the negative of A0 all over 3 times 2. And yeah, I could multiply 3 times 2 and get 6, but very often when we're dealing with power series, leaving your multiplication as it is becomes more useful because we're hoping to find a pattern. Plugging in n equals 2 gives us that A4 is equal to the negative of A1 over 4 times 3. Plugging in n equals 3 gives us that A5 is equal to the negative of A2 over 5 times 4. But of course, A2 is 0, so whatever I'm dividing it by, I just get 0. And we can keep going. A6 is going to be the negative of A3 over 6 times 5 when you plug in n equals 4 into that recurrence relation. But I know that A3 is negative of A0 over 3 times 2. So that means that A6 is going to be the positive A0 over 6 times 5 times 3 times 2. And A7 is going to be the negative of A4 over 7 times 6. But plugging in what I know about A4, this is going to be the positive of A1 over 7 times 6 times 4 times 3. And then A8 is going to be the negative of A5 over something, but I don't care because A5 is 0, and dividing 0 by something still gives me 0. And I can keep going. A9 is going to be the negative of A0 over 9 times 8 times 6 times 5 times 3 times 2. A10 is going to be the negative of A1 over 10 times 9 times 7 times 6 times 4 times 3. And A11 is going to be 0. And so if I have information about A0 and A1, then I have information about all of my coefficients. I get this A0, A3, A6, 9, 12, 15, 18, 21, and so on. Those are all going to be related to A0. 4, 7, 10, 13, 16, 19, 22, and so on. Those are all going to be related to A1, 2, 5, 8, 11, 14, 17, 20, and so on are all going to be 0. All I need is some initial conditions to figure out those first 2 values. That's the basic idea. We work through, we substitute in, we get a recurrence relation. We hope that the recurrence relation will help us do something interesting, and then we proceed from there. I would like you to try one of these, although the entire process is fairly lengthy and honestly not all that enjoyable. I don't want you to try to go through from beginning to end on this first try. So my instructions to you are to set up the recurrence relation. If I scroll up a bit here, remember that this is the recurrence relation. This an plus 2 is equal to an minus 1 over some stuff. That's what I'm looking for from you. If you can get me something that looks like that, then we can work from there and try to see what else is happening. All right. write a recurrence relation for the coefficients of the power series solution to the differential equation y double prime minus x squared y equals 0. Again, I'm implicitly assuming here that we're talking about a Maclaurin series, so it's going to be centered at x equals 0. Um, there's nothing weird that's going to happen on this one. And remember, the recurrence relation means I want to write one of the coefficients of the power series in terms of some earlier coefficient in the power series. All right, so take a couple of minutes, see what you can do with that, and I'll see you in the next video.